Let's do this problem. We've got a spring, and it's stretched from its equilibrium position. Now, equilibrium position means that's when the spring is not stretched or compressed. It's just relaxed. It's not applying any kind of force. And as shown. So here's the spring in its relaxed position. Kind of like spring, kind of like this, maybe. And what we're going to do is we're going to take that spring and we're going to stretch it, and we're going to measure the force on it. And now I took some imaginary data here. That is, I just made it up. And so let's suppose that we stretch a spring, and we have a really hefty spring scale, and we measure the force it takes to stretch this spring 5 centimeters. And so we have these data here. So from these data, I want you to draw a force versus position graph. And then from that, I want you to write the equation. And hint, use y equals mx plus b. Now, draw the best fit, when you draw a straight line, draw your best fit line through it. Don't just use the data. But anyway, and then for part C, I want you to calculate how much work was done to stretch that spring. And hint, it's the area of the graph. Okay. So, let's do it. Now, I tried this last period, and I didn't use graph paper, and I got results that weren't that great. So I'm going to go ahead and use up some of my very precious graph paper. So let's do part A, and we're just going to graph this thing. So here's force, here's position. Now force goes all the way up to 150, so maybe I'll go 20, 30, 40, 50, 70, 80, 90, 100. Oh, I'd started just a little bit lower. So let's do that. And this is what you have to do when you're drawing graphs. You have to say, okay, I'll start here, and I'm going to have this go up to 150. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. So I'll make the origin here. And I'll make this 1, 2, 3, 4, 5. So this is x in centimeters. And then this will be the force in newtons. So 20, 40, 60, 80, 100, 120, and 140. Okay, that looks pretty good. Now I'm going to start graphing. Well, when I had 0 displacement, I measured 0 force. The spring is in a relaxed position. And at 1 centimeter, I got 29.4. So here's 1, here's 20, here's 30. 29.4 is right about there. Oh, I forgot to scale this. And then at 2, we have 60.2 newtons. 2 centimeters, 60.2, or here's 70. So that's right, pretty much right on the line. Can someone close the door, please, over there? Thank you. And then 3 is 90.05, so 91. So just right on the 90 line there. And then at 4, it's 119.6. Well, that's going to be right on, just under the 120, but like that. And then at 5, it's 151. So there's 51 right there. And now you draw your best fit straight line. And yeah, you know what I did. I mean, I made it a little bit over and under. If it was perfect, I want you to get used to that. But if you look at these data, wow, they're pretty good. That's pretty good. Something like that. Okay. Now, one of the things that you should get in the habit of doing for the AP test. Anyway, this is part A, right? So, yeah, we're done with part A. Now, part B, you want to get an expression for the for force as a function of position of stretch. And so, well, I said, use y equals mx plus b. But instead of y, this is the force. And then we are going to figure out the slope of this line. We'll talk about that here in a second. And then what is x? What is the x-axis? Oh, the x-axis is the x-axis. Yay. Okay. Yeah, that happens once in a while. And then plus b. Well, what is the y-intercept here? Oh, it goes right through the origin. So this is 0. Don't have to worry about it. But this is the rise over the run. The rise delta y over delta x. Well, not delta y, delta f over delta x, right? That's the slope, rise over run. So I'm just going to arbitrarily pick 2 points, and I'm going to pick 2 points that are not data points. They want you to do this on the AP test. You are going to get data. You're going to have to get the slope of the line. And if you use data points all the time, they're going to get grouchy when they grade your free response question. So I don't know. It doesn't really matter. I'm going to use 1.5 and 4.5. So that's going to be my delta f over delta x. Well, my final position, I'm going to make that 4.5 minus an initial position of 1.5. Okay. Now I'm going to look up at the 4.5. And 4.5 is right there. And this is, I don't know, 120, 130, I don't know, maybe 130. What do you think? A little under 135. It looks maybe 134. Does that make sense? 134? That's what I get by just looking over here. That's okay. Minus, and then here, I'm going to go up, and I'm going to go over. Well, see, this is 40, and this is 50. So what, maybe 44? I don't know, 44 newtons. Now, I'm just kind of looking at it and guesstimating. So I don't know. We'll see. Oh, this is in newtons. Don't forget your units. And this is in centimeters. That's going to be important in a minute. It's going to be in centimeters. So now I get on my calculator. 134. 134 minus 44 equals 90. And then this is 4.5 minus, so that's 3. And I get the slope of 30. Right, 30 newtons per centimeter. Okay, now what does that mean? That means it takes 30 newtons of force to change the stretch of that spring by 1 centimeter. So each additional 30 newtons of force results in another centimeter of stretch. Does that make sense to everybody? So now I can say, okay, force is equal to 30 newtons per centimeter times x. And there we go. Okay. Now, This, one thing you'll notice that I tried to do here, I try to get kind of cute. Look at my data here. Now, again, I made this data up. But you see how, like, 0, 30, 60, 90, 120, 150. Now, I deliberately subtracted or added from those. Why? Because I'm trying to simulate real measurements where there's a little bit off. There's human error, there's the measuring uncertainty in the measuring tool, and all that sort of thing. And but notice what I did, and I didn't fake it. I drew the best fit line that I could, and I got a better slope than I would have gotten, a more accurate slope than I would have gotten if I just picked 2 data points to do it. Okay, so something big, for the AP test, and it is time. I mean, in 4 months from now, you'll be taking the AP Physics 1 test, and I'll be a nervous wreck. But you don't want to pick 2 data points, especially if the data is a little bit erratic. You want to draw your best fit line, and then take the slope from the line, not from 2 data points. So this is my answer for part B. Now part C. It says how much work was done, and it says hint, how much work was done by the hint. This the area underneath the graph. Well, here's the area underneath the graph, like this. Just shading it in very lightly. But folks, what kind of shape is that? Yeah. So if work is the area underneath a force versus displacement graph, and it's a triangle, you can just say, okay, well, that's 1/2 the base times the height. Yeah? Well, what is 1/2 the base? The base is 5 centimeters. And what's the height? Well, looking at the graph, I don't know, it looks like about 150 newtons. So if I do this, I go, okay, 5 times 150 divided by 2 equals 375 joules? Is that correct? No, it's not correct. What mistake did I make? Well, it's 151? That's not my mistake. When I drew the best fit straight line, I got to 150 here, not 151. Yeah?
The joule is newtons per meter, not centimeter.
Well, we want this to be in joules. That is correct. It does have to do with units, but it's not newtons per meter. What's a joule? 1 joule, I don't know, maybe I misheard you. 1 joule equals what? Am I up? No, I'm not on screen. 1 newton times 1 meter is 1 joule. So what are these in? They're in centimeters. Ugh. You got to write your units down, and when you multiply, you got to make sure that everything is in compatible units. So these are not in joules. These are in Newton centimeters. Now, a Newton centimeter is a unit of work, but it's not a joule. So what do I have to do to it? I'm going to put that over 1, and I'm going to say 100 centimeters is equal to 1 meter.
Now you're off screen.
Thank you. I'm just going to do a unit conversion. You could have done it up here. So that's just dividing by 100, so you get 3.75 joules. So let me come on up here. So it took 3.75 joules to stretch this spring out. Where did that energy go? If I take an elastic material and I stretch it out, can I get that energy back? Is it gone? No, it's stored up. Look what's going to happen. What would happen if I let go? Ouch. See, I'm going to do this. So now here's what's happening. I'm going to transfer energy out of my body by doing work. Remember, work is a transfer of energy through the application of a force from one system into another system. I am the original system, me. Quite a system I have here, isn't it? Now I'm going to pull on this and transfer energy, from these bad boys right here into the stretch of the spring. Can this spring affect change now?
Yes.
Yes, the work that I did on the spring is now stored in the spring. And that's what makes this happen. When I let go, now the spring pulls back and we get that. So that's one of the things we're going to learn about later today is the energy stored in a stretched or compressed. This spring won't compress. It's too tightly wound. But how much work does it take to stretch a spring? And then that's going to end up being the energy that's stored in the spring. And that spring can do work and give you that energy back. Okay. So anyway, there's the question. And here's the solution. Any questions? There will be a problem like this on the test. That is all.